revolutionise optical metrology? Or yours?
Okay, thanks for the introduction. I thought I'd have to blow up the title a little bit to make it at least sound more interesting. It is actually pretty interesting. I have the benefit of having already had a good introduction to the topics of lasers given by the previous lecturer. Actually, he gave a nice introduction on Monday. So I will skip all the how lasers work and so on, and then we go straight to how we can make ultra-short pulses in lasers. I think that's maybe not yet presented so far. And then how to go from ultra-slow, from ultra-fast to ultra-slow. Especially I want to talk about optical femtosecond comms, which indeed actually did revolutionize many fields in optical metrology, and they changed the way we measure and access certain things in physics. Especially, actually, there will be a lot of potential for most likely the next 10 to 20 years. So some of you might actually be affected by it. Especially one big question now in physics is certainly the dark energy, the static system. So lasers actually might be able to help to understand that a little bit better. Another thing which is completely unknown still by experimental tests has not been shown yet whether the fundamental constants of physics are actually constant. You know, the gravitational constant. Physics has a whole bag of constants, and they come out of nowhere, essentially. And so it would be kind of nice to know where they came from. I mean, Einstein made up the cosmological constant. It's a mere fudge factor in his theory. I mean, it seems to be kind of useful, but it comes out of nowhere. And now, of course, dark energy will kind of reuse that concept, but where did it came from? Where did it come from? Are these real constants? If they are not constant, we know we need a model to describe how they evolve over time. The problem is that these constants seem to be constant to at least 10 to the minus 18 change per year. So fractional change, 1 part in 10 to the minus 18 per year. You can imagine that's pretty damn hard to measure. But what you can do now is, with ultra-fast pulses, you can actually indeed make systems that can easily measure stabilities much better than 10 to the minus 18 in principle. And so in the next 4 lectures, I want to talk about the systems you need and how you can actually build something like that. And actually, it's not difficult. As a student, you can build a full metrology system by yourself throughout a PhD career. Within 4 years or so, you can build a system that allows you to measure to a precision, optical frequencies to a precision of much better than a Doppler shift caused by 1 micrometer motion per hour. That's 10 to the minus 18. That's really easy to do. So let me show you how. Before I start, I'm working at the University of Colorado. I chose this place because Colorado is kind of a unique, especially Boulder is kind of a unique mix of course, great outdoors. So if you like Boulder or outdoors, please come and visit us. Another thing is we have NIST, the National Metrology Lab, just across the road. We have Schibli, which is a great AMO physics place. I think it just got voted #1 together with MIT again in the US. And so this is kind of a unique combination of ultra-fast physics, cold atoms, and precision metrology. So if you're interested in these fields, give Colorado a thought for maybe a postdoc or so. If I have time in the end, I would like to talk about some future directions where will the comms bring us. I already mentioned measurement of fundamental constants and their time evolution will certainly be on our agenda for probably another 20 years or so. Okay, so ultra-fast lasers, why and how? And of course, as usual, many interesting things get started over a year in a bar. And so actually the same thing, ultra-fast optics, was pretty much done over a year in a bar. And actually the bet was a horse running in, I don't know actually what kind of, this is not gallop, so there are like 20 different kinds of way a horse can walk supposedly, but anyway, in this way, the question was, does the horse leave all 4 hoofs at one time? And sure enough, you see, now the horse is flying. And so this was assessed by Edward Muybridge in 1878, and I think it took him about 3 years to develop a camera with a fast enough mechanical shot to actually take this movie. And believe it or not, in this time, NSF actually had money, or the British National Science Foundation had money to make such movies. Of course, it works with buffaloes too, and actually, buffalo is the symbol of our university, so I thought I'd show you this one. And especially, please pay attention to the hair, it's pretty cool how that moves. So that's ultrafast photography as about 130 years ago, and of course that's all incredibly slow. What I'm really after now is something of the order of a single optical cycle, which is about 3 femtoseconds in the near IR. So okay, how short is it? Well, it's trivial how short it is. It's 10 to minus 15 seconds. It's a number with ridiculously many zeros in the back, but what does it really mean? So here is a logarithmic scale of time. Here is 1 second. That's about your heartbeat rate, right? You have a 1 heartbeat per second, unless maybe you meet your girlfriend or boyfriend, then this might double, but nevertheless, it's a logarithmic scale, it's probably still about 1 second or 2 hertz maybe in this case. So 1 millisecond, that's about where these pictures were taken. About 10 milliseconds actually was the shutter time. Nowadays you can do 1 millisecond with your digital camera. A little bit shorter was done by the guy who was usually only referred to as Stock at MIT, which is Professor Edgerton. He developed the flashlights, which are mainly xenon flash bulbs with a high pressure, and they allow you to make flashes of light as short as about 1 microsecond. You have a camera with a mechanical shutter, the shutter is open, but then at the moment you want to take a picture, a very strong light of flash is emitted, and you can see a bullet frozen here going through an apple. This goes about at 3 times the speed of sound, so 1 microsecond can kind of freeze such a motion real well. Actually, the same guy, after the war, developed a thing called a Kerr gate. This is a camera that has an optical shutter, and it has a shutter time of about a nanosecond or so. And what you're looking at here is actually an atomic bomb exploding in the desert in the US. Here is a tower. That thing is about probably 30 or 40 meters tall, and you see the first few microseconds of this blast. Once in the last shot, this is already probably 100 meters across or so. Even faster timescales are, for instance, molecular vibrations. They take place of the order of about a picosecond or so. So you have about a terahertz oscillation frequency, and that's still about 1,000 times slower than a femtosecond. And a femtosecond, actually, when you look, for instance, in the classical Bohr model, it's about 100 attoseconds, or 0.1 femtosecond. It's about the classical orbit time of the electron in the hydrogen ground state. But for us, more interesting, that's about 3 femtoseconds or 2 femtoseconds is about an oscillation period of visible light. Okay, so that's how short a femtosecond is. So it's pretty short. But how can we make such short flashes of light? So you saw in the beginning I talked about mechanical shutters, then I talked about flashlight, then later Kerr gates and so on. But once you reach a picosecond, I haven't had any normal daily life object that is capable of actually making such short pulses. And you might or might not be aware of Modoc lasers. Who is aware of Modoc lasers, how they work? Okay, you better be. And you know too, right? Okay, so I will talk about how a Modoc laser works and how that allows us to make something like a single optical cycle and then nothing for a long period of time, and then another single optical oscillation of an electromagnetic wave. There are many applications already, I mentioned some, and actually my passion really is more in the frequency domain application, where we get this insane accuracy in some measurements, where we really can assess things like 10 to minus 18, 10 to minus 21 even has been shown recently. Okay, so this I will skip simply because the introduction was done already on Monday. And so I will go right to femtosecond pulse translation. And so there is nothing actually magical about it. And so you think about a laser resonator, you have 2 mirrors, and the laser resonator gives you kind of boundary conditions of the electric field, right? The electric field has to repeat itself after one full round trip, otherwise you cannot get a resonance. So nothing complicated. So here you have, for instance, one of such modes that fulfill this boundary condition, another one and another one. And of course, if the length of the cavity is L, then you know that the integer multiple of half wavelengths has to fit into your resonator, or in other terms, in one full round trip, 2L, it has to be an integer multiple of the wavelengths of your light. So that's our boundary condition. But nevertheless, we have many ends, right? And it can go from 1 to infinity, so we can in principle have many, many colors, all of which are resonant at the same time inside of a laser cavity. And of course now you know from Fourier series, you can add different ends together, so waves with different ends. They're actually called longitudinal modes because this is usually referred to as the longitudinal direction of your laser cavity. I will not talk about transverse mode because I think already that was introduced on Monday. And so if you line up the phases of those nicely, you can get constructive interference at this point in time, so this would be the time axis or space, no matter what you prefer. But then a little bit away from that, you get a destructive interference and the electromagnetic field drops to zero. And so that's all there is to know about how to make a short pulse. What we really need are many, many of those colors, because the more I add up, see, this is not localized at all, but the more I add up, the more localization I can get. And so if I want to make a really short pulse of light, I need a really huge spectrum. And that's actually where the problems really come in, because lasers you might know of as a device that emits a very nice color. Here I have a laser pointer, again it's a frequency doubled neodymium vanadate, as you have learned yesterday. It's a Chi-2 process going on in this small box. It costs like $20 or so. It's kind of impressive, because if you try to make that in the lab, it's probably $2,000. So what we really need is a laser amplification medium that can amplify many different wavelengths at the same time. And in the previous talk you saw there are dyes, for instance, in the LC laser we've seen just before the break. These dyes allow you to actually amplify across the whole visible range. We are not so interested in dyes simply because they have other drawbacks and it makes it a little bit hard to work with for our purpose. So what we are more interested in are solid state materials, or as you will hear, I think today or tomorrow, are about fiber lasers, which also allow you to actually get many, many colors amplified at the same time. Now here is a boring laser. It only oscillates with one color, but nevertheless the cartoon means here I have an amplified medium and a set of laser mirrors which allow me to get the feedback I need to produce laser light. So if I combine these two now together, well, boom, I get many colors out of my laser, but unfortunately when I add this up, I get the black line, and the black line doesn't look anything like a short pulse, it's just a noisy output. And so that's not enough. Having many, many colors at once does not give me a short pulse. Well, why? I need to have this constructive interference at one point in time. And so I must make sure that the phases of these different colors are by some means synchronized with each other. And so magic happens. I put in some phase locking element which actually makes sure that the phases of all these colors are nicely synchronized. Well, what the magic element is, I will show just on the next slide, but essentially it lines up all the phases. Now what I have is an electromagnetic field, this black line is the sun, bouncing back and forth between the laser mirrors. Every time it hits the output coupler, which is simply a laser mirror that has a few % of transmission, I couple out a small fraction of that pulse, and so I get, after every round trip, I couple out another short pulse from the cavity. And the interesting thing here is, these pulses are all copies of that one pulse inside of the laser cavity, and therefore the electric field knows about the electric field in the other pulses. And so it's some sort of a coherent train of pulses. This is very different from having a flash lamp on your camera. If you take two pictures, the phase of the light emitted by the flashlight has nothing to do with the previous pulse, and so there is no phase coherence whatsoever. But here these are all copies of the very same pulse that survives every round trip, and it's just whatever I couple out gets re-amplified here, but you know a laser works because this is kind of a cloning process, so the photons I lost, they get recreated here with the same color, same momentum, and same phase. So these are all coherent pulses. This will be important in tomorrow's lecture. Of course, actually what we also do need is some means that make sure that all these different colors propagate exactly at the same velocity. Otherwise, after one round trip, my nice phase coherence will be destroyed again, because maybe red and blue, they travel at different speeds, as that's usually the case, for instance, here in the window of the door, that glass, different colors propagate at different velocities. Maybe some of you might be a little bit too young, but Pink Floyd was kind of popular when I was a student, and so they had a t-shirt with a prism on it, and the effect that you actually can split white light into many colors is because they propagate at different speeds. And so this is a problem, for instance, we have a laser medium in there, and that makes that different colors will propagate at different velocities. And so now the biggest challenge to really get to very short pulses is to get a phase compensation over a very, very large bandwidth. And that took a long, long time to actually achieve. So I will talk about this a little bit in more detail. As a preview for tomorrow's lectures, I want you to pay a little bit attention that now we have these many, many colors, and we have a boundary condition for each of these colors. We have made sure that they are going at about the same speed, and then we have a phase locking element, which makes sure that the phase, the relative phase between these pulses is fixed. And so it turns actually out that if I plot those different colors in the frequency domain, they have perfectly even distances between each other. So if this is 100 megahertz between these two lines, this will be exactly the same 100 megahertz over there. And this has been proven to 10 to the minus 21 accuracy. And so that's kind of the magic of these precision measurements. But I will talk much more about this tomorrow. And actually, 2005 Physics Nobel Prize went to, in part to this one, and Chen Ho is at our university. Okay, so this phase matching element, so this is kind of the easier part to actually make the laser go. And the phase matching element is something like a saturable absorber, meaning you can saturate the loss of this thing. So at low light intensity down here, this is a pretty lousy optical element. It has a lot of loss. But now if I hit it with high intensity, the peak of the pulse, it saturates by some means, and so it becomes more transparent. And of course for the lasers are actually like students a little bit. We want to go the easiest possible path. Of course there's even a Fermat's principle, but anyway, the laser wants to do that too. And so the laser prefers to concentrate all its energy into this intense pulse, because then it has less loss, it feels less resistance, and naturally the laser will start to form a pulse. You can also imagine this is a positive feedback mechanism. So if I have a perturbation, this perturbation will get amplified more than the rest. And that can actually lead to problems, which I will not discuss today, but you can imagine that there is some issues we have to take care of. In the time domain, you can imagine the situation like this. So this is the intensity of my laser pulse as a function of time. Say this is a few 10 femtoseconds or so. I have the gain, which is more or less constant if I work with a solid-state material, because solid-state material, the lifetime of the gain is typically of the order of at least a few microseconds. In fiber lasers, it can be as long as 10 milliseconds even. And the pulse round-trip time is only nanoseconds, so nothing big happens to the gain on a single round-trip. But now when my pulse hits this saturable absorber, the saturable absorber reduces the loss, like we are out here now. And so it gets actually amplified only in the center of the pulse, and in the wings I have a net loss. Now you can imagine I have a long pulse. It gets amplified only in the center, but not in the wings. So I cut down the wings, I stretch the center, what I end up with is a shorter pulse. And so every time that thing, that pulse, goes through the saturable absorber device, it gets shorter in time, shorter and shorter, until I reach kind of a balance between pulse shortening due to this effect and pulse broadening due to the imperfect dispersion compensation, which lets my pulse drift apart again. So there are a bunch of saturable absorber devices around. For us, there are mainly two of interest, and one of them, which is which was found by accident actually in about 91. So two guys building a titanium sapphire laser, they suddenly noticed a very weird behavior of their laser because their laser suddenly wanted to produce pulses, and the pulses were much shorter than anything they had in the lab to measure them. And actually, it turned out these pulses were already about 100 femtosecond short, which is incredibly short if you expect to build a continuous wave laser. And so what happened is whenever the laser started to act funny, the mode, the transverse mode changed. And so from this they concluded it looked like as if somebody would put a lens in the cavity, changing the transverse mode structure. And so that lens was actually a curve lens, and I think you have heard about Chi-3 processes so far, or Chi-2 only? Yesterday? Chi-3 too, right? Only Chi-2? Okay, so anyway, the next one is Chi-3. It's not very inspiring, but you can imagine after Chi-2 comes Chi-3. And so what that does is, it, as a one effect you can get from it is that the refractive index increases when you have high intensity. He mentioned that yesterday, right, in his lecture. So the laser beam itself has a higher intensity in the center than on the outside. Here with the green pointer, we cannot really see that well, it's too bright. But typically the laser mode has a kind of a Gaussian intensity profile. So in the center it's more intense than in the wings. That means in the center the refractive index of my medium here is higher than at the edge of the beam. And that's exactly what a green lens does. A green lens is typically a cylindrical block of glass, but you dope something into the center so that the refractive index is a little higher in the center. And that leads to a focusing behavior of that medium because the light actually propagates a little bit slower in the center than in the wings, and so the phase starts to act like in a collimating lens. If I have a high intensity now, I can actually make sure that all my light can pass through an aperture, just a hole in space. But the low intensity light, for instance the wing of the pulse, does not see that effect very much. You remember it's a very weak effect, typically 10 minus 20 or something, or picometers per watt or something like that. So it's a weak effect. So I can make sure that my wings get clipped here, but the center of the pulse can transmit without loss. And so the effect again is I get a long incident pulse, I get a shorter pulse out. The pulse is now a little bit weaker because I actually have loss, but no big deal because I can just amplify it again in my laser medium with the next round clip. Another one which we use also quite often is a satchel absorber based on semiconductors. And in a semiconductor, that's kind of a little bit of a fancy two-level system, more or less. You have a valence band where all your electrons are usually. If I shine light on it with enough energy to actually create the electron hole pair, this electron will live there for a certain amount of time, and then it will recombine. But since we are talking on femtosecond scales, they are pretty much sitting there doing nothing for this period of time. And if I have enough light, I can populate about half of all the available states up here. So I don't get a population inversion, but I have same densities of states here and here. So the probability to get the next photon absorbed is exactly the same as the probability to get the next photon spontaneously emitted, so doubled, meaning the semiconductor simply becomes transparent. So if you have a thin semiconductor film, it might be totally black, you don't see through. But if you have very high intensity, it becomes transparent because of this effect. So you are blocking further absorption because you have a finite density of states, and you already populated half of them, and so it becomes a transparent material. These things are usually incorporated into a mirror, and of course everything is grown with some complicated epitaxial process, but you don't need to worry about it. It's essentially a thin film of this kind of semiconductor on top of a highly reflecting structure. And then you have an incident light coming, it interacts with this. If it's weak, it gets absorbed. If it's very intense, it gets reflected. And here is, for instance, a measurement of such pulses, such a device. For higher and higher intensities, I get more and more reflectivity in this device. So here is the change of reflectivity. And then after about 150 femtoseconds, it starts to partially relax. This is actually because the electrons here scatter among other peers, and so that I get a thermalized Fermi-Dirac statistics again, and the electrons will be very hot. They will be 10,000 kelvins or something. And eventually they will relax down into the valence band, and that's this long, typically picosecond to nanosecond tail. Okay, so how can we use such a device now? Here is a very simple free space laser. Free space because the beam is actually propagating in free space as opposed to fiber laser as you will hear tomorrow. The laser consists of the output coupler mirror. Of course we need that thing because that's where the pulses actually come out, or the light comes out of the laser. Then the light is trapped inside of this resonator, and here is the other end mirror, so it will go back and forth between these two end mirrors here. One end mirror is now this CSEM. This is a short acronym for semiconductor satchel absorber mirror. This has been established now for about 15 years or so. And of course, inside of the laser cavity, we have our optical amplifier, and the gain is higher if you have high intensity, so we want to have a very tight focus inside of there. So that's why we have curved mirrors to produce high intensity in the center. And actually, this is the place where we have really high intensities inside of the material. And you can imagine that inside of the material, we get now these curve lengths as well. And so some lasers actually don't have this part at all. They just use the curve lengths that's spontaneously formed inside of the amplifying medium. So here is, for instance, a picture laser I made a couple of years ago for some strange application. But so again, you have output coupler mirror. The laser light goes back and forth between these mirrors, and here I have the semiconductor absorber that forms the pulses. This was not a particularly short pulse, but it was a particularly low power laser. You can operate it on 2 AA batteries for probably about 2 days, and it makes 100 femtoseconds. So kind of good. The smallest laser I've ever made, mode locked, is 8 millimeters long. It's just a crystal, and the semiconductor absorber is pressed right to the crystal. And on the other side, I have an output coupler, which is transparent for pump light, and then I get pulses in this device and laser output. The problem with these kind of lasers is they require insanely high amount of power. And I think I pumped it as high as more than 100 watts peak, and the average power is 50 watt pump. And you can imagine putting 50 watts in a few millimeters of crystal leads to big problems, and so you have to get rid of it by overcooling and so on. So it's not very practical, but I think probably in 10 years or so we will be able to make such a device the size of a laser pointer as well, which would be kind of cool. Without going into details, because you will hear much more about that tomorrow, are also fiber lasers. They have become increasingly important for optical comb generation. And the last 5 or 6 years or so, actually more, 6 years, we have been pursuing femtosecond fiber lasers for combs. And it seems they will actually eventually take over the solid state market simply because they're significantly more robust. The idea is exactly the same. You have semiconductor absorber mirror, for instance, here in this cavity. Then the light, instead of going through free space, is propagating through the fiber. Then I have some semi-transparent mirror at the other end, which allows me to output couple the light. And of course, the pump light is then also coupled into the fiber and is absorbed in this doped fiber. The last system is really the current system. You see here output coupler mirror, 2 curved mirror, amplifier medium, and here the currents occur. So I have no semiconductor absorber in here, but I have added some mirror pair to compensate the dispersion in this material. So together with this mirror pair, I want to have the same speed of light for all different colors. And the occurrence occurs here, so only the center of the pulse gets amplified. And about 9 or so years ago, we achieved spectra as wide as nearly an octave and pulses as short as about 5 femtoseconds, which is about 1.6 optical cycles or so. So very short. Okay, actually, how can we measure such a short pulse? Just as a little side note, to measure a short pulse of 5 femtoseconds, I mean, even a fancy stopwatch will not get you anywhere close. An oscilloscope will not get you anywhere close. Sampling scopes cannot go much faster than typically tens of picoseconds or a couple of picoseconds. So how can we do that? And of course, the trick is, again, you use the femtosecond pulse to measure the femtosecond pulse. since it's hard to get two exactly same femtosecond pulses, all we need is the beam splitter. I have a femtosecond pulse coming here, half of it travels this way, the other half travels that way. I can move this mirror just mechanically, 1 micrometer more propagation of light, speed of light, that's about 3 femtoseconds. So if I move that guy by 1 micron, this thing gets delayed by about 6 femtoseconds. Then I have a nonlinear crystal. This is now a Chi2 medium, which you now all know very well about. It makes the second harmonic light, so it adds 1 photon from this arm, 1 photon from that arm. You can imagine momentum conservation has to work here as well. So here I have a k vector pointing this way, h bar k up here, and so the sum of the two has to be exactly in between the two. And so all I have to do is I put an aperture here to cut out the individual beams, and I can detect the sum frequency that only occurs if the two pulses are overlapped. So when I move the two pulses over each other, I get high second harmonic light. If they are not overlapped, I get no second harmonic light in that center. And indeed, what you see on the screen when you move this delay line, that's the delay line position, you get really the correlation of the pulse itself. So that's an easy way to measure pulse. You could also make it in a Michelson configuration where you actually have interference as well, and that's kind of useful if you have really, really short pulses. It's not very useful if you have long pulses, but if your pulses have only a few optical cycles in it, that's kind of an easy way to actually assess them. By the way, I want to point out, if you're interested in this kind of stuff, give the Encyclopedia of Laser Physics a try. You can Google that, Encyclopedia of Laser Physics, or RP Photonics. That's actually a company that provides that, but it's free for your use. So it's really a nice resource. I copied these pictures out of there, which are easy to understand certain concepts in laser physics. Do you have any questions so far about pulse generation? I will have another 50 minutes, I believe, so, but I think it's just a good place to ask some questions before I continue. Yeah?
You showed the thing with the cosmic correlations and some of the width of the pulse. I was just wondering, how could you see from the graph how long the pulses were? I mean, you said 2 pulses, and so how do you determine exactly which one?
Yeah, so here in this picture it's a little bit easier to understand. So here I have 2 pulses, and the second harmonic light that comes out here relies on the fact that I had a photon from this side and a photon from that side, right? I get second harmonic in this direction, but that's blocked on the aperture. So whatever goes through my aperture, I know it came from this side and from that side. Now, if I move this stage, I can separate the 2 pulses in time domain, so they can never actually make a photon that comes out this way. And so as long as they are not overlapping, I have no light coming onto my detector. I only have light as long as they are overlapping. And so from this, I know this is the overlap region of the 2, and that's exactly mathematically the correlation function of the pulse itself, because it's a copy of itself. The correlation function, you know, it's unfortunately not possible to report. So if my pulse is asymmetric, I will still get a symmetric correlation. So I have to know a little bit more to really get the pulse. And so these 2 methods are easy to understand, but they are not the best ways to measure pulses. But other methods will take another hour of talk. But is that more clear now?
Yeah.
Do you have some other questions?
Yeah, I have a small question. In order to get a short pulse, you do want a wide bandwidth.
Yes.
In order to get the time down the product, which is conservation of energy. But we're using the CSAM technology, you're using a reflector which narrows the spectrum.
For the CSAM it's an issue, but for the really 5 femto or less, like 3 femtosecond pulses, we don't use that. We use coordinates only.
Okay, right.
And actually the big problem is then to make the mirrors, to make it work. And so I will talk about the mirror technology in the next lecture. The CSAM technology has a problem. The CSAM technology is usually based on specific semiconductor materials, so it can be narrow absorption bandwidth. Another problem is it's usually made on top of a semiconductor mirror, which is a Bragg mirror, and they have only a very limited bandwidth. But another thing we actually did a few years back is we used carbon nanotubes that allows you to choose any absorption bandwidth you want. And we spin coated a polymer that was doped with carbon nanotubes onto a classical laser mirror. So you can combine ultra broadband mirrors with ultra broadband absorption. And we got 5 optical cycles in a Irving glass laser. 45 femtoseconds. So it's a 1.5, so it's a long difference. So CSEM, the classical CSEM, is not so good choice. But there are some, I think the record is around 6.5 femtoseconds with a CSEM. Still pretty short. All right, other questions? Yeah.
You mentioned that the saturation of conduction layer and valence layer are same. So we don't have more electrons in conduction layer. So how this emission is induced?
Oh, I see. You don't have gain. Okay, nothing to write here. But in a two-level atom, if the atom is in the ground state and you shine light on it, the photon will be absorbed, it will be in the excited state. If I have an atom in the excited state, I shine light on it, I have a certain probability of getting stimulated emission. So I get 2 photons out for 1 photon in. In the other process, I get no photon out for 1 photon in. So if I have now the same number of atoms in the excited state as in the ground state, I have exactly the same probability of absorbing a photon or having stimulated emission of a photon. And so the statistics just gives you transparent medium. And so in the semiconductor, we don't have a two-level system, but we have many states. Maybe that's going too far back, but we have many states that can be occupied. On average, I have the same density populated or empty. That's exactly the same as having a big ensemble of two-level atoms. And so the medium really turns transparent. I don't get amplification, but I can turn off the loss. And so that's also the reason why you cannot make a laser with a two-level system, because you can never invert it by shining light.
Maybe you have your mind a bit closer, because I guess there are some problems with
Like this? Or maybe on the nose?
More than that.
All right. Is it better?
somehow I don't know if that works. Is it turned on?
Oh, we can do this application between the session. Yeah,
I see.
we could move forward.
Yeah, maybe afterwards. Okay. So actually one thing that's really interesting to note with the ultra-short pulse generation is the first laser was demonstrated exactly 50 years ago now. And only a very short period later, passive mode locking, that's the process which I just explained, was demonstrated 1965. And it yielded about 10 picoseconds, which is already really short. And then there was a big race using these dye lasers. Dyes, as we have seen before in the previous talk, dyes are good because they have a large emission bandwidth. They are not so good because they are kind of messy to work with and they have some noise issues as well. But in terms of short pulse generation, dyes really ruled the planet for a long time. Of course, after the dynasty of the dinosaurs a few years later. But nevertheless, they really ruled the planet for a long time. And actually, these are kind of a little bit cheating because these are pulses that are not generated inside of the cavity, but they are generated outside of the cavity by shortening a long pulse with some nonlinear optic strips. Again, Chi3 process is the keyword here. Then the blue lines here represent solid-state lasers, and solid-state lasers are so much nicer to work with. If you walk in a lab with a dye laser, you have a very noisy pump that is actually required to pump liquid dye, so dye dissolved usually in methanol or something, around, because it bleaches out really fast. It bleaches out typically in a few milliseconds. And so these dyes were pumped around under high pressure, high velocities were required. And so whenever a hose broke, you had dye all over your body, and actually everything shorter than about 600 nanometers, these dyes cause cancer. So I'm not sure how many physicists from this era are still on here, maybe nobody in the audience. But I've seen people with lab coats with all sorts of colors over it, so it's kind of messy. And solid states were so much nicer. This is kind of solid state technology. You can carry it around, no problem. It's more efficient, and actually nowadays we reach also pulse durations that are actually shorter than the shortest ones done by dyes. I think the best record right now for external compression is about 2.8 femtosecond for visible light. And then for attosecond physics, the shortest light pulse ever made so far, which was confirmed, was about 120 attoseconds. So pretty short. If you're interested in the history of this kind of thing, I summarized some of this work here a couple of years ago. So here, the 90s was really the era of titanium sapphire, which is kind of a wonderful solid-state material. It has very good thermal properties. It has a very large bandwidth comparable to dyes, actually. And so it was really important thing to develop the short pulse lasers. Until 92, the development was kind of slowed down and stopped at about 30 femtoseconds because of the optics they had. The standard optics were mainly Bragg mirrors. You remember, you have a kind of a photonic band gap by having an alternative layer stack of quarter waves, so you get reflection, but the reflectivity bandwidth is really limited by the refractive index difference of the two materials, and you only have such and such many choices, usually like silicon dioxide and titanium dioxide, but you never get really large bandwidths out of such mirrors. Then people actually tried hard, brute force, use silver mirrors. They have very large bandwidth, but they have a lot of loss, and things didn't work out that well, but nevertheless, 10 femtoseconds were possible. Another problem now people realize is really the dispersion compensation. At 10 femtoseconds, you struggle a lot to get the dispersion compensated well. And so then there were some ideas, chirp mirrors and double chirp mirrors. This will be subject of the next lecture, to create much shorter pulses. And you see actually this initial dramatic reduction of pulse duration. This is a logarithmic scale. This dramatic reduction and improvement eventually leveled out. And it looks like all this effort, actually here, I know from here to here, we spent probably $500,000 to improve this result. So it doesn't look very impressive, but when you look at the spectral width these lasers created, it's a totally different story. So here is the fractional bandwidth created by those lasers, and these improvements kept growing steadily throughout the last decade, and actually with the invention of double chirp mirrors, it essentially went to physical limitation. So this is a full octave of spectrum. Okay, of course, if you are kind of addicted by short pulses, you want even shorter pulses, right? And so one trick is you take a long pulse, because that's easy to make. 30 femtoseconds is already nearly a continuous wave for us nowadays. So you take a 30 femtosecond pulse, you stick it through a nonlinear medium, a Chi3 medium, which is maybe a piece of glass or something, because everything has essentially Chi3. And then afterwards, you try to compress the pulse by fixing the spectral phase that got screwed up in this process, and you can actually make really short pulses. I think now actually this result improved about a year ago by this group in University of Hokkaido to about 2.8 femtoseconds. Another approach we actually also pursued about 7 years ago is we take two sub-2 cycle lasers with totally different colors. Then we make some nice electronic box to actually synchronize them on an attosecond time scale, which is kind of fun. And then we take these two beams and we interfere them, and essentially we created a single optical cycle this way. Nevertheless, it's a rather complicated system, but it's fun to do something like this just to see whether it works. And it does work. Okay, so here is the story. 22 femtoseconds, this is kind of the electric field you need to make that 3 femtoseconds. That's about a single optical cycle at 900 nanometers. Okay, so since I like short pulses, let's make a half cycle. A half cycle at 900 nanometers is about 1.5 femtoseconds. Is that a good idea? Can I do that? You all have E&M classes already. Can I make a pulse that has only half an optical cycle? It would be great, right? Because I can make short pulse. Maxwell equations. So when you study physics, you go through a rigorous training of Maxwell equations, which is a nice set of complicated differential equations with some solutions. And Maxwell equations, one thing you find out when you solve it, you remember you can bring it into the form of a wave equation, which is easy to solve. But the wave equation tells you that the DC part does not propagate, because that's a Coulomb field. It's a DC electric field. It does not transport energy. So only the AC field is what transports energy. So if I have a laser beam, I want a traveling wave. DC is not a traveling wave. And so I cannot make anything that has a DC component. Everything shorter than a single optical cycle will have a DC component. So I'm stuck with that. If I want less in time, I need to go to shorter and shorter wavelengths, and that's the field of attosecond physics, and I'll talk about this if I have time in the last lecture as well. I think it's time for coffee.
Okay, great. So back here at 11:25. So I've only got a few minutes. 9 minutes.